Hey guys, lesson 812 day 1 is all about double and triple roots, and really we're getting a lot more into being able to sketch polynomials just based on the factored form of their equation, and also just being able to look at a graph of a polynomial and write the equation for that graph. So the big things that you need to be thinking about for this section are the end behavior and the x-intercepts of your graph. And when I say end behavior, I am talking about when I have a graph, and if it looks like this, my end behavior is what's going on right over here and right over here on the ends of my graph. So it's exactly what it sounds like. And that's what we talked about earlier this week. And the roots, x-intercepts, the factors, that's where we hit the x-axis. Okay, those are going to be super important in what we are doing today. So before we get into the new double, triple root stuff, we want to make sure that we're solid on just regular roots here. So if I give you an equation like this in factored form, we want to go ahead and find all this information and use it to sketch a rough graph of this function. So for the leading coefficient, we have to look for whether there's any numbers squished with these x's or any numbers up here. Really, we don't actually care what the number is, we just care if it's positive or negative. Now, there's no numbers, so really the leading coefficient is 1. But what's important is that it's positive. If there was a negative sign, then we would have said it was negative. The degree is the highest exponent on the x. So the way we figure that out is we count, can't talk today. The way we figure that out is we count how many x's are being multiplied together. So we have 1, 2, and 3 x's being multiplied together. So my degree is 3. That's an odd number. All right, now end behavior, we use that table that we referred to. Let me pull that up. All right, so here we can see that we have some combinations of leading coefficient signs and degrees. So if we go back to our problem here, we have a positive leading coefficient and an odd degree. So positive and odd goes with down, up. And behavior, you know, they meet here. So down, up is what we're going to be going with here. Let's go back to blue. Ooh, it got thick again. All right, so that's my end behavior. And the next thing we want to know is the roots. So for roots, we want to go ahead and look at these factors and just take the numbers inside of them for their opposites. It's kind of like if we were solving and setting it equal to 0. So x plus 10 is going to give us a root of negative 10. X plus 7 will give us a root of negative 7, and x minus 12 will give us a root of positive 12. All right, now that we have those, we can go ahead and label them on our x-axis here. So we'll put a negative 10 there, we could put negative 7 here, and we could put 12 all the way over here. All right, so this is where I will cross the x-axis at these 3 points, and we're going to use our end behavior to help us figure out exactly how that should look. So I know that my end behavior is down, up, which means that our graph will start down here because the left side should be facing downwards, and it will end facing upwards on the right side. So I know that our graph will look something like this, and it's not going to be beautiful, but it's fine. All right. So that's something like what our graph would look like in this case. Okay, and again, we know it looks like this because we know these are where it crosses the x-axis, and our end behavior should be down, up, just like these arrows indicate. All right, let's do one more of these before we move on. So we have 4 factors here. Our leading coefficient is going to be positive again because there's no negative sign here. Degree, we have to count how many x's are being multiplied. 1, 2, 3, 4. So this is a 4th degree, which means it's even this time. End behavior, because we're positive and even, let's go take a look. Positive, even, that means I'm going to have up, up end behavior. Okay, and my roots come from these, so plus 6 gives us a negative 6, plus 3 gives us a negative 3, minus 5 gives us a positive 5, minus 8 gives us a positive 8. All right, and now we're on to the step where we can just label those on our axis. So we have -6 here. I'll put that here. -6, -3, 5, and 8. All right, these are approximately where I think those would fall. And I know my end behavior is up, up, so I'll start up here. And it doesn't really matter how low I go. I don't know how low the graph does go, but I don't really care much either, because it's not going to be that precise. I just know that it, goes up in that direction and goes down in these directions. So this is around what our graph would look like if we were to graph this on Desmos. Okay, but obviously it's not going to be perfectly accurate because we don't know the exact heights of these peaks. All right, so that is how we would go about graphing based on just these regular roots. The new thing for today is when we have double and triple roots. So here in this polynomial, we'll notice that the x plus 5 factor is being squared. In this example, we also have a factor that's being squared, and we got to see what happens when we do that. So I've got a Desmos here, and before I talk about that, I want to go back and draw your attention to the fact that in our two graphs that we drew here, every time we hit or touched the x-axis, we just went through, and then we just kept going with our graph, right? Through. Now, over here, we'll notice that in this graph, at the x plus 5 factor, which was squared, that brings us to an x-intercept of -5. Now, instead of going through the graph like we're used to, it actually happens to bounce off the x-axis. And that's something that occurs when you have a squared factor. Okay, and if you look at the graph for this one too, let me turn this off. This one has a squared factor, and at -3, which comes from that factor, it also bounces, right? So every time we have a squared factor, which we're going to call a double root, that's when you know it should bounce. So we know that double roots look something like this. Okay, and that bouncing spot is the x-intercept that has that part. Okay, and a way you can remember this is that, we talked about parabolas a lot last semester, right? And parabolas have an equation x squared, right? Just like our double roots. And the graph for a parabola looked like this, right? It bounced right off that axis. And so this is a way you can remember. If you remember what the graph of a parabola looks like and that a parabola is x squared, it could kind of remind you that you're supposed to do this bouncing action just like a parabola does. All right, or kind of like this. Okay, so now let's explore the triple root. I have also graphed the triple root here. Let's turn that off. Triple root, something really interesting happens when you cube a factor. At this factor that's been cubed, x plus 4, we have an x-intercept of -4, or a root, and you'll notice that it like flattens out, right? So that's actually something called an inflection point, which you talk a lot about in calculus. But what that means is that before your curve is kind of concave down, it's facing downwards, and after this point, you're facing upwards now. The curve is concave up. And when you do this flattening stuff, that's your inflection point. And this is what happens whenever you cube a factor. Okay, so if I drew my example here, you would look something like this. Flatten out here, and then look like that. Okay, and then this is the spot. It's not the best picture, but that's the spot where it flattens. Okay, that's really ugly. And similarly, just like we had a trick to remember the double root, for triple root, there's a trick as well. If you remember our cubic function, which happens to be cubed, just like our triple roots, the graph for that looks like this. Right? It did the same flattening action that we're seeing here. So if you remember these parent functions from last semester, that will be helpful for you. All right, so let's do two examples here. One example, we're going to use the equation to draw or sketch the graph, and the next example, we're going to look at the graph and use that to write the equation. So here, let's look at this equation. We see that our leading coefficient, we don't have any negative signs sitting out by the x's or outside, so it's going to be positive. The degree, well, let's count. There's two x's here because it's being x squared, and then there's 3 here, and then there's 1. So you do 2 plus 3 plus 1, that equals 6, meaning it's an even number. So we have an even degree of 6. End behavior, we have even and positive. Even and positive, that gives us an up end behavior. Okay, and my roots, opposites of these numbers, so -10, -7, and +12. All right, these roots probably look familiar from the last page of this note sheet, but this time we have different exponents, so let's see how that affects our graph here. We've got a -10, -7, and a 12. All right, so drawing our curve, we know it's going to be up, so it has to start high and end high. So we'll come down, and before you start drawing, you kind of have to notice what's going to happen at each spot. At the x plus 10, which gave us this -10 root, it's been squared. So this means that over here, it needs to bounce. That's what happens with a double root. With the triple root at the -7, it should flatten, because that's what happens when you have triple roots. And in this one, it just goes through straight away because it doesn't have an exponent, or it has an automatic exponent of 1. So let's follow those rules. So it comes down, bounces here, and then at 7, it does this flattening action. And then at 12, it just goes straight through. Okay, and that's about what our graph will look like here. It's not perfect, but it's a decent sketch. All right, now let's go to this example. We've been given this beautiful graph and we want to write an equation. So the first thing you want to do, honestly, is just notice where it hits the x-axis, right? We've got -1, 1, and 2. Now, right away, I can actually go ahead and start writing my equation. If I have a root at -1, I know I'll have a set of parentheses of x plus 1, right? Because we're working backwards. Here, a factor of x plus 10 gave us a root of -10. So if I have a root of -1, I'm going to have a factor of x plus 1. Okay, this positive 1 will give us a factor of x minus 1. And the last one, positive 2 root, will give us a factor of x minus 2. All right, so now all we have to do is figure out the exponents. So this one flattens, so it's a triple root. So that means it's going to have an exponent of 3. Because this root goes with this factor. This 1, it goes straight through, no trouble here. So this one doesn't actually need an exponent. You could put an exponent of 1 if you wanted, but I'm not going to. And then at the 2, which goes with this factor here, it bounces. So that's a double root right there, which means I need to put an exponent of 2. All right. And so that's it. We've written our equation. We can go ahead and fill in this other information now too. We know the leading coefficient is positive. There's no reason for us to believe it's negative. If it was like down, then we would have known it flipped. But the degree, well, this thing already told us it's a 6th degree, so there's that. We know 6 is even. But even if you didn't know, you know that there's 3 x's here plus 1 plus 2. So if you add those, you get 6. The end behavior clearly is up and up. All right, and that is it. Go ahead and try those open math problems and, reach out if you need help.